In this lesson, we'll discuss learning target number 1, explaining the process of dissolving chemicals and the factors that affect the solubility. In order for a solute to dissolve in a solvent, they must attract each other through compatible intermolecular forces. This gives us the general rule of like dissolves like. Solutes that have charges on their structure will dissolve into solvents that also have charges. Nonpolar substances will only dissolve in nonpolar solvents. Solutes must also be more attracted to the solvent than other solute particles in order for the solvent to separate out the particles and dissolve them. The first step to figuring out if something will dissolve would be to draw the Lewis structure of the compound, determine the types of bonds it's held together with, and what type of compound it is, and then ask yourself, is there an intermolecular force that can be formed between the solute and the solvent? If there is a fairly strong intermolecular force, then the compound will dissolve. Here are some examples showing that process. The first example asks us the question, does CH3Cl dissolve in water? The first step is to draw each of these compounds. Here are the diagrams for both molecules. CH3Cl contains a polar C-Cl bond. It's also a polar compound because I can draw a line separating the charges. This compound can attract other compounds through dipole-dipole forces. We're going to go through the same step for the water. Water has polar OH bonds. It is also a polar compound. Now water, because there's H's directly attached to O's, can attract through hydrogen bonding to other waters. But if it's next to another polar compound, it can also attract it through dipole-dipole forces. And this is what we have in the situation with CH3Cl. The slightly positive H on the water can form an attraction between the slightly negative Cl on the CH3Cl. We have a common compatible intermolecular force between our solute and our solvent. So does CH3Cl dissolve in water? Yes, it does. Try out the next example on your own. Does CH4 dissolve in water? Go through the same process. Draw a Lewis diagram of each compound, figure out what kind of bonds it contains, what type of compound it is, and what type of forces it can make. Then ask yourself, is there a compatible intermolecular force possible? Here are the diagrams. The bond between carbon and hydrogen only has an electronegativity difference between 0.4. So these are all nonpolar bonds. making this a nonpolar compound. Now, nonpolar compounds only attract through London dispersion forces. We know from the previous question that water has polar bonds and is a polar compound and can attract through hydrogen bonding or dipole-dipole attraction. Notice that there is no common intermolecular force between our solute and our solvent. That means that CH4 will not dissolve in water. The first two examples prove the like dissolves like rule. In the first example, CH3Cl, we have two polar compounds. Because they are the same type, a solution can be made. But in the case of CH4, we have a nonpolar compound and a polar compound. Because these are not the same, one molecule has no charges and the other molecule has slight charges, there's no attraction and no solution is formed. The last two examples show ionic compounds. Here's the structure of our NaCl. It can also be written like this. NaCl has ionic bonds because I have a full transfer of an electron between a metal and a nonmetal. That makes this an ionic compound. And it uses ionic forces to stay together. Now we know from the previous questions that water has polar bonds, is a polar compound, and can be held with hydrogen bonds or dipole-dipole attractions. Now at first glance, our solute and our solvent don't have an intermolecular force that's in common. But through your life experience, you know that sodium chloride dissolves in water. Looking at the structure, this still follows the like dissolves like rule. We have a compound that has charges dissolving in a compound that has slight charges. Because both structures have charges on them, there's a force of attraction between them. The 1+ charge on the sodium can attract the slightly negative charge on the oxygen. Also, the slight negative charge on the chlorine can attract the slightly positives that are on the hydrogens. When an ionic compound dissolves, the ionic force holding the Na and the Cl together actually gets broken, and the ions separate and become independent. Water molecules can then orient themselves around the ions so that you get full charge, slight charge attractions. I'll represent water molecules using green boomerangs. Remember, water is a bench-shaped molecule. At the point, we have slightly negative oxygens, and on the ends of the arms, we have slightly positive H's. Because sodium has a full 1+ charge, the slightly negative part of the water will be attracted to it. Now, water can be attracted to the sodium on all of the sides. And actually, because we're dealing with a 3D chemical, it can attract in front of the screen and behind the screen, because water's boomerang shape and flat, and a whole bunch of planes in between. So a lot of water molecules can attract to a sodium ion. The opposite orientation happens with the chlorine. Because it's a negative charge, it will attract the hydrogens. Again, also in all three dimensions. So a lot of water molecules can attach onto a chlorine. Now this is a new type of intermolecular force. It's known as an ion dipole attraction. The definition of an ion dipole is the force of attraction between a fully charged ion and the slight or partial charges of a polar molecule. In terms of strengths, it is not as strong as an ionic force, but stronger than hydrogen bonds. So there is a force of attraction between our solute and a solvent. But I just told you ionic forces are stronger. Remember, in order to dissolve, the solute must be more attracted to the solvent than other solute particles. Because more than one water can make an ion dipole force with the sodium and the chlorine, the ionic bond between the Na and the Cl can be broken. It's like the saying, one ant can't, but many can. Because there's a compatible intermolecular force here, both my solute and my solvent have charges. The NaCl will dissolve in water. In the last example, you might think the same thing happens. Here we have an ionic compound, calcium phosphate, and we're trying to dissolve it in water. We can represent the calcium phosphate using this simplified structure. A calcium 2+ ion and a phosphate 3- attracted together using ionic forces. I'll again represent water molecules with green boomerangs, with a slightly negative oxygen and 2 slightly positive hydrogens. Around the calcium, the oxygens for the water will be attracted using ion dipole forces. And around the phosphate, the hydrogens will become attracted. Now, if you have a look at the charge difference between the calcium and the phosphate, this is a pretty big charge difference. There are 5 integers between these two charges, representing a very strong ionic bond. In the previous NaCl example, there was only an integer difference of 2, a 1+ and a 1-. That represents a weaker ionic bond. In this case, the ion dipole attractions between the water and the ions are not strong enough to pull this ionic compound apart. Because the intermolecular forces between the solute particles are greater than the attraction between the solute and the solvent, calcium phosphate will not dissolve in the water. Now, how do you know when the ionic bond is too strong for the ion dipoles? You can always check the solubility table on the back side of your periodic table. As soon as it says that a compound is insoluble, it means that the ionic force between the ions are greater than the multiple ion dipoles that can be formed with the water. How much of a solute will dissolve in a solvent, or its solubility, depends on two external factors. The first being temperature. You need to be careful though, because temperature affects different solutes in different ways. The solubility of solid solutes increases with temperature. For example, coffee. The reason why we use hot water to make coffee is because the molecule caffeine, which we're after, has a low solubility in water. The hotter the water, the more caffeine dissolves and the stronger your coffee. The solubility of liquid solutes is not affected by temperature at all, so when you're dissolving a liquid into a liquid, it doesn't matter what temperature you do it at. However, the solubility of gases decreases the warmer your solvent is. This happens because as you heat up the solution, the particles inside of it speed up. The increased molecule speed forces the gas particles out of the solution. An example of this is when you open a can of pop or a bottle of pop. Warm pop fizzes more than cold pop does. Another example is the effect on fish. In warm water, there's less dissolved oxygen, so fish have to breathe faster. In some cases, where industries take water out of a stream or a lake, there are special regulations of what temperature the water needs to be before it's dumped back into the stream. This is known as thermal pollution. If the water returned to the stream is too hot, it won't have enough oxygen in it, and the fish downstream will die. The second external factor is pressure. The solubility of solids in liquid solutes are not affected by pressure at all, but the solubility of gases are. As you increase the pressure, the solubility of the gas increases as well. An example again is in pop bottles. When you buy a bottle of pop, it doesn't fizz. That's because when the factory closes the container, it pumps in a high pressure of CO2. And as the pressure increases, more CO2 dissolves in the pop. When you open the container, the pressure drops drastically, and so does the solubility of the CO2. As the solubility decreases, the CO2 leaves the solution and forms bubbles. This can also happen if you're a deep sea diver. You may develop a condition known as the bends. The deeper you dive, the more pressure the water pushes on you, and the greater the solubility of gases in your blood. The longer you stay down there, the more gas dissolves in your bloodstream. If you come up to the surface too fast, the pressure will drop too drastically, and bubbles of gas will form in your blood. If they form in your abdominal muscles, then you bend over with severe cramps, which is why the condition is known as the bends. If a bubble forms in your brain, it could cause a blood vessel to explode and give you an aneurysm, resulting in death. So deep sea divers come up very slowly in a process known as staging. They come up a little bit, hang out for a little while, and see what the effects are. Then come up a little bit more, hang out at that level for a little while so that the pressure on their body decreases gradually and it allows the gas to come out slowly instead of forming bubbles like opening a bottle of pop. In the next class, we'll perform lab number 1. For homework today, I want you to draw the diagrams for the substances in the chart, iodine and calcium chloride. Then figure out what types of bond it has and what type of compound it is, and also what intermolecular force it can have. In the lab, you'll mix these substances with water, which is a polar substance, and mineral oil, which is a nonpolar substance. Make predictions of what's going to happen. Will the iodine dissolve in the water? Yes or no? Will it dissolve in the mineral oil? Yes or no? The same for calcium chloride. We've also given you the structure of glucose. Look at its structure and use what we've discussed in the course to figure out what type of compound it is. Is it ionic, polar, or nonpolar? And what force it can make. Then predict, will it dissolve in water or in mineral oil. When you come to class, your teacher will check your diagrams and then you can perform the lab.